somebody hasn't signed in yesterday, anybody here? You too. We can just go in the back. It's just yesterday, so hopefully you remember what it is. You can use the front row too, I don't spill. You have my voice, right? Sometime I don't. Good morning. Thank you for being on time. We'll try to start on time. I'm sure this weekend with a few people coming in, and that's okay. It's always a little more tricky with the video, so when you ask a question, I'll try to repeat it, so it's not completely ignoring people looking at it remotely. At the same time, you guys are the priority, so if you have any questions, feel free to interrupt. You probably will not lose my focus. I'll still cover what I need to cover, you don't have to worry about that. Perhaps as just a starting point, I have been doing consulting work with Professor Eager since 2002. So that's 14 years. He and I won't necessarily attend each other's lecture, but we have a good feeling. We've been doing this class for about 4 or 5 years together. So we know, I know approximately what he's going to cover. We won't see an exact match or an exact link between the two modules, but his topic of material selection takes a very broad topic, as you'll see. And I will be a little bit more specific. So what we're going to cover together are material indexes, so a little bit how you end up selecting between steel and all the other competitors, including composites and plastics. So the idea is to specifically talk about preparing for service. So if you want to use a material in service, there's a lot of work to do. And probably a lot of you have been involved to some extent or have seen engineering drawings. I'd like this piece machined this way, and then these two pieces put together. Please put a good weld there so it's all good. Well, that's the very basic version of a processing or manufacturing specification. But there's a lot of good ways to do this, to refer to codes and standards specifically. Say, you're going to do the welding according to this code. So you don't have to tell exactly everything that needs to be done. So after we go through talking about the performance of different categories of materials, we'll talk specifically about the kind of things you need to include. Let's say you want to use a steel. You could call it an AISI 1020. So that says the chemistry of the steel, but you know, maybe you also want to have some minimum mechanical properties. In that case, you'd use an ASTM designation, for example. So we'll go a little bit into more details on things that are very important to include, and all of this is with examples. So this is probably one of the last lectures that I don't come with samples. I'll be bringing samples to the class and we'll try to go through them. I see most of you as new faces, so I think there are a few repeat students, but most of you are new. What's the proportion grad versus undergrad? So that you're supposed to raise your hand on one of those two, by the way. So undergrad. Okay, and grad? Good, thank you guys. So it's very clear that you are taking the course by interest because you're all here today, and we want to honor that to the extent, again, that you have questions. There's something like, oh, well, this doesn't seem very clear. I can try to go too fast sometimes, so whenever there's a question, I think it's good to go over that. So with respect to the outline, the next step here, demand versus capacity is really what design boils down to. So you put a calculation on paper, you say, well, you know, I think this is going to be my load, this is the geometry, so it should resist those conditions. And then you look at the material you're going to use. So is the material able to sustain the impact or the types of loads or the environment that I'm going to subject it to? So we try to balance this and make sure that for foreseeable conditions, you're not going to have a failure. So that's an area where in different industries, it's treated different ways. If we think about the car industry, for example, they don't really, it's not necessary for them to calculate very precisely the load and all the components in a car. They do a lot of design verification and optimization by testing. They just shake the whole car, and that's considered sufficient. Now, if you're looking into aerospace, for example, you have to shake the whole structure, yes, but you also need a very detailed calculation that says, well, you know, according to the maximum deflection of the wind, the load is going to be this much, and my safety factor is this much. And to some extent, it's an advantage because you know you're not over-designing on your aircraft if you've done the analysis. If in a car, sometimes there's some components that are just bigger than they need to be because nobody ever really realized this section of the frame doesn't see the loads that another section of the frame sees. And a lot of it also is manufacturing. You don't have the ability to mill out material where you don't need it, which is something that we do a lot in aerospace. So it just varies again in industry. The last topic for this semester is failure analysis. So I will teach you some of the basic concept of taking a broken piece and figuring out roughly what happened. Was there pre-crack before it fractured, or there wasn't anything wrong and it just overloaded, for example? So it's something in general students find very interesting. If you do have something broken and you want to bring it up, we can also do that. I have a lot of different pieces from over the years, but it's always fun to look at something new. I get more excited. So, we can do plastics, ceramics, and metals. If you graduate students here in the class, if you have something in your thesis that you're working on, we can go over that. For today, it's just an general introduction. I'll talk a little bit more about what I'm doing, and then we'll go through a few examples in these three categories of material performance index, specification, and then failure analysis. So I came here for my PhD about 15 years ago, and I worked for Schlumberger in the drilling and exploration research division. So they were all about
wear resistant solution to go 5 miles down and then 3 miles sideway to do all the directional drilling. And what directional drilling means to them and other people in the industry is you have a steering function, so you have pads that will allow you to, as you drill, to continue to orient. So if you have the little red pads here, you have 3 of them around it, and you have a stabilizer in the back, and you just actuate these as you turn to change your orientation. It's very, very precise. And you also have a lot of sensors built into this head, the drilling head, that collects information about the formation as you are drilling. So you have a drilling plan, and then you're going down, and if it's not exactly like you thought it was, maybe you'll go 30 degrees this way and then go back down again. And so it's a very, very elaborate process. Some of the most expensive operations may run for a few $1 million a day of operational costs. So if you're drilling for a month or 2 months, it just adds up. So everybody that does these things now have MBAs, not just engineers, because of the money involved in all the operation. So it gave me a little bit of a flavor for what I want to do. So I came back and did my thesis and started thinking, well, you know, I want to do something related to wear in mechanical resistance and all that. So I worked at nanostructured materials in Post Street. It was new back then to have, grain sizes between 2 and 15 nanometers. So I was doing essentially a scratch experiment on the surface and characterizing, relating the behavior with the mechanical properties. At this point, it's so long ago that I think I can talk about it more. One issue with the experiment here is I was testing a material that was very hard to begin with. But because the experiment here essentially is, instead of doing nano indentation, which you've probably seen in the nano lab, the nanomechanical lab, at the end of the infinite corridor, instead of going down to a sample here and creating, let's say, triangular indent, what I did, and we're still doing, but now it's for a more practical test instrument, is going down and then sliding. And of course, we don't use a conical tip. That would be too hard to, it's not a pyramid, it would be too hard to align it, so we have cones and sphere are the 2 main geometries that we're using. And that profile here is essentially starting down, you see the hole. So when you indent, you actually go a little deeper because you don't have that pileup. What happens during the test is if you have your undeformed surface and it's a cone tip, you build material on each side. That's what we call pileup, right here. So you have a penetration depth, but you also are lifting up a lot of material here. Now, the amount of material you pile up relates to consolidation. So if you have wet snow and you're doing the test, you permanently won't pile up that much. If it's a flurry, it's going to pile up a lot here on the side. So the idea is to make that distinction. If we can identify material that have a lot of work hardening. So by work hardening, just refresh your memories, talk about the stress strain curve, and we have the elastic behavior. When it starts to yield here, your stress starts continue going up. Now it could be going up a little, or it could be going up a lot. If it's going up a little, it's a little bit like a flurry. And if it's going up a lot, it's like wet snow. So what happened during the test, you can see all these whitish, bright orange piles on each side. So this was very high, just like this. And that meant very low strain hardening. So to this point, the best explanation for that is when we were deforming the nanostructure it had grain growth. So we went from nanometer grains to much bigger grains during my test. It's not that great for wear resistance. It means that if you are going to touch the surface, you will lose some of the characteristics that you put in the first place. So I guess the short story is I didn't write a lot of papers about nanostructured material. I really focused on the test itself, these experiments and relating it to the stress strain curve. And that was fine. Ultimately, I graduated. I worked for a consulting firm, a little bit like Exponent, for 5 years. And I've had my own consulting. Professor Eager also is involved with this, and also have a startup company now for 2 years. So it's, you know, different things. I could speak to you if you wanted about academia versus industry. We had these panel discussions sometimes that are very interesting. I think in the end you do what you feel like you're better at. For me, it wasn't to do the scientific research, it was to actually go and, you know, apply some of the concepts. I feel that there's a lot of knowledge we have that is not used when it's time to actually build stuff. That's been my point of view for a long time. It hasn't changed one bit. So, talking about building stuff, the different things, and we will cover all of this in this class to some extent, is you go through the design and selection of material. If you're building a special car or off-road vehicle, anything like that, you come up with a way that will perform the function very well, and you have to manufacture it in a good way. Then you test it, and you may or may not analyze it. That depends on the application. So let's go to design first. This is new information about the Dreamliner. It's not officially from Boeing, but I think we can use it as a starting point to say in commercial aircrafts, we have been using more and more composite. So this figure used to be, the 777 is not that old of a design, only had 12% composite, and they moved up to 50. So there are a few things to say about that. The first one is aerospace is a very, very slow moving instrument. Back in year 2000, I worked for an airframe manufacturer, Bombardier, and we were considering using some of those composite, the great year for the fuselage. But we were essentially, because, so what happened a lot in aviation and in commercial aircraft is the big manufacturers, Airbus and Boeing, are going to be the first one to adapt something new because they have this competition between the two of them. They deal with the biggest aircraft, so the ones that are more expensive, and they will do the R&D if there's R&D to be done. And then after one of them, Airbus was the first one to adapt composites, and then Boeing said, okay, fine, we'll do it too, and they went a little bit more non-linear. They went from not using a lot of it to using a very large quantity. So from that point on, the smaller aircraft manufacturer, the original jet people, the 50, 70 seat, 100 seat, will start picking up and adapting some of those technologies. So if you're making 100 passenger aircraft, chances are you won't be, the first one to implement the material. It's just the way it is. So that's about kind of who's going to do it. Now, the time it takes, 10 plus years. And the composite is a good example. It was fully proven 10, 15 years ago, I would say 50 years ago. And they started putting one panel and then maybe two, and for flight tests, but not for selling commercial aircraft. And then the part of the reason is, when we're talking about material and process specification, if you want to be super safe, you just get a copy of their spec and you get your stuff built with all these requirements of qualification of the people, the processes, the documentation, it's unbelievable. There's a reason, because we want this to be very reliable, and we don't want to just trust that people are gonna do what they say they're gonna do. So, I think there's a lot to be learned there, so we'll try, when the topic is appropriate, this is mostly going to come in when we're talking about material selection, the whole aircraft aviation business. The reason they can work a lot of different materials is it's a very low fraction of the overall cost of making an aircraft. So this is a little bit outdated, but it gives us a little starting point. So on top, materials, 3% of the cost of ownership of an aircraft. Okay, so even though steel is, very affordable, I don't really mind if I make the 3% 1%, but end up changing my weight. So the weight here is about 3 or 4 times more important than the cost of material. Related to weight, you have fuel, and that of course varies from one year to another. So fuel is 1/3 of the overall cost. Maintenance is very big, so if you have to inspect more and you have more sophisticated way to inspect because you have composites that are very hard to look at, well, guess what? This is gonna go up, unless you make a design that doesn't need inspection, and that's sometimes very difficult. So there is a big drive to be innovative to some extent, but the time to do it is just very, very long. So if you arrive with a new material today, in our case with our startup, we have a new testing device for mechanical properties. Well, it's gonna take 10 years, we may as well try to do something else with it in the meantime, right? So we're not planning, you know how to make an airplane? No, okay, you're not interested? Okay. Anything, we should talk a little bit about the difference between the engine and the airframe. It's very, very different design when we get to that point. And I think it's, good, because talking about something that we can all relate to, the good thing is you go home and you'll remember it. All right, we'll talk about the Longfellow Bridge now. Hopefully you know about that. It's been in repairs. Does anybody know that? Okay, good. You live here. Some people have been, I think the first year I was on campus, I don't know if I figured out there was a problem with the Longfellow Bridge. Everything is more narrow. So it's supporting the Red Line service, which, is probably our best MBTA line. It's been there since 1908, and that's a time where apparently in the Boston area there were only very few cars, so it was still horse and carriers. So it was kind of overbuilt for that generation, but things have changed so much. When we started using cars, going faster and faster, all the salts and modern things that just didn't exist back then, real car traffic jams and all that. So since it was fabricated, and that's just a view of how they're building the arches. I picked it out just because you can see this is the primary structure, the arches, and they connect to the different piers. So you have a lot of redundancy in that bridge. That's not a problem. The problem a little bit is you only have 4 members to hold a train, out of these arches, and if one of them goes, then it's no good. So you go from looking very, very safe to something like, well, we don't really want too much corrosion, and yet we do have a lot of corrosion. So the one reason why they started talking, and they had a budget approved to work on the Longfellow Bridge, I would say 8 years ago, and it's still not done. There are a few reasons for that. Is nobody will, in terms of politics, wants it to go on their budget. So, they wanna come up with the idea, but then they don't wanna pay for it. It's public work. Another aspect is, there's a big incentive, there's a good reason as well, so to try to preserve the architecture. It is an historical structure, we don't have that many of them, so the idea that we'll just take all of that out and make a modern bridge hasn't passed, if you will, the public opinion. So the idea has been to preserve the appearance. Now, in the context of the class, let's talk a little bit more about that, the appearance. They didn't know how to do I-beams, so in modern days, a lot of the construction use a design like this, so as a single piece that's formed, and I'll bring one to the class that's done different ways. This is a single piece of steel. It's great in bending. So if you apply the load this way over a length, your material, you have a lot more material in the fiber than in the center, so it's efficient in terms of the weight and the cost. So they couldn't do that back then. They could do angles. So the basic structure for the Longfellow Bridge is a bunch of plate and angles. So you have the web, let's say, and then if you want to make that structure over there, now you need to put an angle here, an angle there. I've seen cases where you have 2 or 3 plates for redundancy as well. Whether it was justified or not, it was kind of the early days of working with steel for a large structure as the primary structure. So yeah, you do this the same top and bottom, you have all sorts of structures, and it takes forever to do it. But they are doing it. This is probably not done in Cambridge, but they had to rebuild a few sections, primary sections, and once it's painted, you won't really be able to tell whether this was done recently or in the old days. Just talking about this, there are a few exceptions. So when you look at the bridge, yeah, okay, so we see the main arch here, and we can all agree, okay, we want the rivets. I mean, sometimes it may not be as well as efficient to make an I-beam and just stick some buttons on it. So it will look like it was, I'm sure somebody thought about it. But anyway, they decided to do it the hard way, the old-fashioned way. And it just speaks to how we've been using materials differently. If you do a riveted connection, the good news is, as long as you put the rivet in, it's great. If it's all put in and compressed, looking back to that image here. This is a solid piece of wrought steel that's in there. As long as it's there, it's not going anywhere. It's not like a weld that wasn't done the right way and could be very brittle, for example. So the chances of making a mistake in the process here would be picked up just by visual inspection. And that's not the case with welding sometimes. You just need to know more, you need to control the process better. So, I think in modern days, we could be less at risk for process variations if we had stick to the old ways of doing things. But there are so many reasons to do things differently. And that's why I do want to emphasize the different ways you can specify for bolted connection, for welded connection, things essentially that do come into almost every large structure. Yes?
Is Longfellow Bridge like a restoration? Are they using the same techniques when they first built in the 1900s and the same materials? Or are they looking to use composites or change the structural?
Okay, so the question was about the Longfellow Bridge and the materials use. It is modern steel, so they didn't try to go back to the more preliminary way of purifying the steel, for example. But in terms of the assembly, they decided to go ahead and use plates and angles. So it's a new way, a new standard for the plate itself. But the shape is the same, and the riveted method, well, actually, it hasn't changed that much. So you could say it's the old process for making it. Yeah. They will use modern coatings to protect it. And but I was surprised because if I was involved with this now, I think about galvanizing it in the first place, and I don't know if they're going to do it. It will make a lot of sense, so you don't have to go back after 20 years to paint anything. It's historical preservation. Otherwise, we would not be going through all that trouble. We'll have welds everywhere. You weld it, and then you galvanize it, and you put it for 50 years, no maintenance. So there's no composite in the primary structure. For bridges, for cost reasons, we tend to stick to steel and concrete, reinforced concretes. There's been a lot of discussion about using composites, it's just too expensive. But the way we use concrete is really as a composite, and we should probably, touch on that. Yeah, I haven't done that before, but it would be fun. There was something else that popped in my mind. Anybody else? Thank you for the question. Yeah, I mean, that's the best way. If I get to participate a little bit in the first class, we're really gonna have a fun semester. The World Trade Center is not a nice event, and I'm bringing it up. It's been a while now. We passed the 10-year anniversary, so that's good. Bringing it up mostly because I want to teach you a little bit that when we're talking about failure analysis, so sometimes we'll be talking of failure analysis in the context of a dispute. So somebody was building something and then it failed and it cost them more money and they wanted to recover that, or somebody got injured, which is really unfortunate. But the concept of failure analysis goes way beyond that for engineering. It's the way we're able to make products and structures. If we never failed at building a bridge, we wouldn't know how to build a bridge. The same for a building, same for a car. There's just so much iteration between the design, the manufacturing, and the failure and the analysis that it all goes back together, including the World Trade Center. So we know it all happened very quickly in a couple hours. The towers were just completely down. The people who designed it couldn't see the problem with just an aircraft going through this. It held at the beginning, and then the discussion was, okay, there was too much heat from burning the fuel. Okay, so that's where a little bit things got started, and then there were a lot of discussions about why is that so important? The steel is embedded in concrete and all those, and it's true. So it's not the primary columns. The columns were protected. So in terms of the failure analysis, I was on the team. NIST was kind of under the control of a lot of the government-based failure analysis. And one thing that they commissioned the company I worked for was to analyze these floor structures. So if we think of the entire building from the top view, it had a lot of big columns around it to hold it in place. Now, one problem is how it was connected here between the columns. So opposite column were sort of connected together through the floor structure. So they, for weight and cost saving, they had these trusses or joists that were connecting to make the floor between the main elements on each side. Well, by the way, this was probably a year before they came up with really what happened. And we're just trying to go through it, kind of knowing the answer, but, so that's not fair, but we don't have, tremendous amount of time. So they probably start with the columns. I wasn't involved back then, and then they start with the idea, well, maybe it has to do a little bit with the trusses that were making the floors. Okay, so you look at them, it's a very optimized structure. You have concrete on top and you have your steel in the underfloor. It's got so many advantages. You can run pipes and wires between those floors, no problem. There's plenty of room, very easy to put the HVAC and the plumbing systems. Great. Now, what happens when you have a fire? How long is it going to take you to heat up just a few inches of steel? Very little time. So very quickly, that structure from the other side was getting heated up. What happens to steel when it gets heated up? It doesn't melt right away, but it softens. So by the time it softens, what you have is it's pulling. So if you go from here and you say all of this now is sagging just like a wire, now all of a sudden, like you have a clot line, and that's pulling. And you can see on the image the building wall caving in. And not just on one side, on the different sides. And that was in between the floors. So the only real explanation that came true with this was we never thought that those beams, those little pieces of iron, were going to be heated. Just didn't think of it. But they did, and they were connected very strongly to the columns. They didn't have to, but they were. And there you go, coming down in 45 minutes. Nobody had thought of it even right after. It just took a long time to go back to the drawings, look at exactly what happened. So in the context of the class, when I said we're going to look at fracture surfaces, it's because they have information that you just have to live with. What's on the fracture surface tells you what happened. It's not your mind or anything else. The same way here, you can think of the building, well, it's made out of concrete and steel, so probably the problem is the steel. Yes, okay, so that's good. Which steel and why and what we're going to do about it. So the fire protection code for buildings has expanded, I don't know, the relevant section probably expanded by a factor of 2 because of 9/11. And for good reasons. If you're going to put something high up, we know now we need to design for a situation like this. And there are multiple ways. One of them is you can say these connections are just going to give up if there is heating and softening. So you make them weaker, and there's one floor that comes out. Okay, big deal. That's one solution. The other solution is to not really have these thin steel members that are uninsulated. Now, it's not practical to think of insulating this. So you have to go to a design concept that has a lot more components embedded in concrete, for example. And then the few supporting steel members are well insulated. That's doable. So those are the two main solutions that were thought through. Because again, people went through to find out exactly what happened, and it wasn't easy to prove. You know, we had to put in some assumptions about the amount of softening of the steel to know whether you had enough pull force to get the beams to cave in. It's, you know, in other words, you can arrive with what you think happened, but it's good if you can also prove it to yourself and others. So, you know, it was a very unfortunate event. We don't want things like that to happen. When we're thinking about cars, that's why there's a lot of road tests done before they, well, you hope there's a lot of load tests done on cars before every generation release, and then you realize with all the recalls that, yeah, no, they've done it a few times, and then you just say this was not a major change, so we're not gonna do it again. So and that speaks, I guess, to the issue of quality control. As an engineer, you have your say to this, but ultimately it's not just you, right? There is a certain expectation that if you drive a car, the wheel won't come off. But, you know, it could be that your navigation system just doesn't start, and that actually happens, right? So different functions will have different level of expectation, and we have to design for those expectations. It's not reasonable to say, like, when we were working on the rebuild of this, the Liberty Tower in New York, you cannot make it foolproof. There's always going to be, you know, a certain level, it just won't resist the demand. And somebody has to set that limit because it's got so many implications with respect to cost. So, I don't know, if we went back to the time that they were doing the Twin Towers, I'm sure this probably was discussed. What if a plane hits? Okay, well, you know, we'll do this, do that, make it strong, and then we go, and that's the end of it. The reality is, they never really analyzed it in details. They never crashed a plane into a big building to know what would happen. And therefore, they didn't think about it long enough. Now, maybe that's the reason, and I've been trying the past couple of years to extend a little bit the section on fair analysis. And Professor Eager also brings in a lot of examples that actually helps you to think the same way. You know, a lot of people have done mistakes. Do I need to make the same mistakes? Hopefully not. You know, hopefully you can do better than what the other people have done. So how do you do that? You get educated, right? That's why you guys are here for. And you gain some experience. So when you're thinking about your project for the semester, there is, of course, sometimes a little tendency to say, well, you know, I've done something that seems to fit in the class, I'm just gonna adapt it. That's fine, you know, but I think that it's an opportunity for you to get a lot of feedback from Professor Eager and myself into either trying something completely new or just going a lot deeper into what you've already looked at. Things that relate to, you know, senior year project are great, and a lot of times you'll come back into something and just learn a whole lot more. There was a big crane collapse I was involved with back in 2007, and 200-300 broken pieces, the whole field, it was over half a mile, was going across the Grand Canyon. Well, you know, where the Hoover Dam is, so whatever that river or canyon's called. There were a lot of towers on each side, a bunch of cables. It was used for construction. So you have the entire dam, and you're trying to bring material to it to build up a new bridge. We thought we had most of the information. You know, everything was sort of adding up. This is a very weak point. and it failed. It seems like it all crumbled, and probably started right here. And that was the extent that we could push our analysis. Now, there was information later that there was a big holding mechanism for a cable that did let go, and in a dynamic way, so that the locking just popped out and unraveled that wire. Now, the problem there was whether the load came from unraveling that big cable or just the wind exceeding a certain amount was leading to the same crumble of the towers that we focused on. So it was kind of, so the second, the question became like, is this the first or the second event, the crumbling of the very weak? Well, if the crumbling of the very weak point happened, it will not lead to as much of a dynamic effect across the canyon on the steel. There's no way. Everything is soft and bouncy, so there will be an effect, but not a very sudden loading. Now, there was a beam just like this one, literally this high, 3 feet high, that did have a brittle type of failure right here that I couldn't understand. I showed it to a lot of senior engineers. I don't understand this. I don't know why we have this. But it wasn't enough, you know, just looking at this and seeing, well, you know, this was dynamically, I couldn't, so there was a piece of unexplained evidence, if you will, in our entire scenario. And it's after that that I personally learned that the rapid loading came into that beam first from breaking up the ratchet. So then all the pieces came together. But I think that the bottom line there is you don't know ahead. You know, the idea that, you know, we would not have issued a report because we didn't examine all the ratchets, you know, was not reasonable. So I guess it's one example where even though we were trying very hard, we were not exactly complete. Now, you try to have these situations not happen very often, but when you doing these failure analysis, the evidence is what's most useful because you have to explain it. So in this case, we had to explain that there was a very rapid fracture there, and we just couldn't. So to some extent, we kind of knew there was something there. We just didn't know what it was. And I wasn't in charge. I was the first year out of school. So I hope you'll like it. I always welcome feedback, and with respect to the term project, I'm not here at MIT full-time, so you want to let me know, like after class, you say like, oh, you know, I'd like to meet with you, you know, can we meet now, can we meet sometime this week? So I'm happy to do that. If you have anything that you're trying to build for a project or just want to talk about anything, I mean, I'm available. That's the reason why I lecture. I want to help you guys. I need to learn more actually about how to brag. So just because I've done, I worked on the Deepwater Horizon for the equipment manufacturer, so that valve that didn't work, I called them up and I said, you know, do you want some help because I worked on this thing? They hired us. So for 2 months, we were nonstop trying to gather the information, and there's a lot of that that's actually public at this point that I can talk about because there's a lot of government studies and things. One of the issues was in the drilling operation, you have a little pipe in the center in a well bore, and the idea is you pump down fluid through the inside of the pipe, and it comes out through the bigger hole, and you have circulation. So most of the time, you have a hole and you have a tool in it. Now, closing that is not very easy, because you can say, oh, I'm just gonna cut everything up, but that's not very practical, because your tool drops and you don't know if you're gonna be able to pick it up again. It may get stuck. So they have all these blowout preventer that will seal around a pipe, and I'll show you some examples of that. But it's not easy. You have 10,000 PSI pressure of fluids. That's 100 times plus what you have in